Goals of the lessons. Students will be able to solve problems that involve distinguishable permutations, use the combination and permutation formula, explore combinations, use combinations to solve counting principles, and understand words such as at least and at most with counting problems. Solve the following warm-up problems. Pause the video while you're doing this. The answers to the warm-up problems are on the next page. If you want the solutions and not just the answers, you should go to the filled-in notes on Haiku. We learned in the previous class that with permutation, order matters. In warm-up number 2, you had to arrange the letters in the name Michael to find all the word possibilities, but there were no repeats in his name. What would you do if you had a word with repeats? We will explore that in the next example. In order to find the distinguishable permutations in a word with repeat letters, you must first figure out how many ways to arrange all the letters in the name to begin with. In the name Rebecca Tourette, there are 13 letters. So in the numerator, we need 13 factorial, because that's the way to arrange all the letters in Rebecca Tourette. However, when there are repeated letters, such as the fact that there are 2 R's and multiple C's, you must divide out by the repeated letters. So in this case, our repeated letters, we will write them all out and find all the options. So our repeated letters are R, in which there are 2 of them, E, which there are 3 of, C, which there are 2 of, and T, which there are 3 of. These are the letters that occur multiple times in the name Rebecca Tourette. Since they are multiple repeats, we need to divide out by the way to arrange those letters. Well, the way to arrange 2 R's is just 2 factorial. The way to arrange 3 E's is just 3 factorial. The way to arrange 2 C's is 2 factorial. And the way to arrange 3 T's is 3 factorial. We must divide out by these arrangements. So we're going to divide 13 factorial by 2 factorial, 3 factorial, 2 factorial, and 3 factorial. In simplifying this, using your calculator, you end up with 43,243,200. That's all the different possibilities and the way to arrange the name Rebecca Tourette. As stated in the previous example, distinguishable permutations are permutation problems where there are repeats. You must divide by the way to arrange the repeats in the problem. So if a problem had 10 letters, you would do 10 factorial, or if the problem had n letters, you would do n factorial. And the repeated letters, suppose you had letters n1 represent the number of letters that repeated, and n2 was the number of letters that repeated a second time. You would need to divide out by the way to arrange those repeated letters. So n1 factorial, n2 factorial, and so forth. So anytime you deal with a distinguishable permutation, you need to divide out the total number of repeats for each element. Now solve practice 1 on your own. The solution will be in the next slide. You will now do an exploration where you try to figure out the number of study groups possible with 5 students. Suppose 5 pre-calculus students, Bradley, Jake, Riley, Natalia, and Lincoln, are trying to form a 3-person study group to study for the next assessment. They are wondering how many different study groups are possible. Write down all the possible study group options. Record your strategies and study group possibilities in the space below. Note, Bradley, Jake, and Riley is one possible study group, but Jake, Riley, and Bradley is not a new study groups. You must have different people in your study groups. Pause the video and work on this. After you have finished the first part of the exploration, check on Haiku or the notes with a peer to make sure you have all of the possibilities. How is the study group problem different than a permutation problem? In a permutation problem, order matters. In the study group problem, order didn't matter. What happens to the study group problem if Nenda joins? Can you solve the problem without writing down all the possibilities? Well, think about it. We talked about how this is different than a permutation problem because order doesn't matter. Since your study group is 3 people, you need to divide out by the way to arrange 3 people. So if you treat it like a permutation problem, it would be 6p3. However, you need to divide out all the ways to arrange those 3 people because order doesn't matter. So in this case, 6p3 divided by 3 factorial is 20 study groups. What you have done is solved what's called a combination problem. A combination problem is where order doesn't matter. As previously stated, a combination is where order doesn't matter. If you're going to do a combination, you're going to do an arrangement of n elements taken r at a time where order doesn't matter. 10CR. This is the same formula that we used with Pascal's triangle. So if you think about the study group problem once Nenda is joined, 6C3, which we already know how to solve, is 20. If you look at the original problem when there were 5 pre-calculus students, 5C3, if you were to solve this on your calculator, that's in fact 10. Example 2. A standard poker hand consists of 5 cards dealt from a deck of 52 cards. For reference, a standard deck of cards has 4 suits, hearts, diamonds, clubs, and spades, with 13 cards in each suit that go from ace through 10, plus a jack, a queen, and a king. How many different poker hands are possible? Well, since we have 52 cards and we are dealing out 5 of them, and since we're dealing out cards, order doesn't matter. The order in which you deal out the cards is not important. To figure out all the possible poker hands, we just have to do 52C5. When you do that on your calculator, 52C5 is 2,598,960. If you wanted to simplify it using permutations, you would write 52p5 and then divide out by the way to arrange the 5 cards being dealt out, which is the same thing as 52c5, which is 2,598,960. This example, you're forming a 12-member swim team from 10 girls and 15 boys. How many different 12-member teams are possible if the team can be a mix of any gender? Well, since you have 10 girls and 15 boys, you have a total of 25 people. And we need to create a 12-member swim team. Well, if you're creating a 12-member swim team, order doesn't matter. So we need to do combinations. So this would be 25C12, which is 5,200,300. Remember, this is a combination problem because order doesn't matter. You have your same 12-member swim team that you're choosing from 10 girls and 15 boys, but this time you have a different situation. How many different 12-member teams are possible if the team must consist of exactly 5 girls and exactly 7 boys? Once again, order doesn't matter, but this time you're picking specific people for your team. You need a slot for girls and you need a slot for boys. In fact, this problem uses both combinations and the fundamental counting principle problem. Since you have 10 girls, and of those 10 girls, you're going to have 5 on your team. So you're going to do 10C5 or 10 choose 5. Now for boys, you have 15 boys that you're choosing from, and you're only going to choose 7. 15 choose 7. Since your swim team is 12 members, you're going to multiply them together because we need both the 5 girls that are chosen and the 7 boys that are chosen. When you multiply 10 choose 5 times 15 choose 7, the result is 1,621,620. This example is similar to the last one, except this time you're choosing exactly 8 girls and exactly 4 boys. So once again, you need your slot for girls. This time we're choosing 8 girls, and your slot for boys, this time we're choosing 4 boys. So from our 10 girls, we're going to choose 8. So it's going to be 10C8. And from our 15 boys, we're going to choose 4. 15C4. We must multiply them together to get the total number of people for our swim team. In this situation, that makes 61,425 possible swim teams that consist of exactly 8 girls and 4 boys if you start with 10 girls and 15 boys. Now complete the following practice problems. The answers are on the next slide. Now complete practice 3. The answer is on the next slide. The following example is very similar to some of the combination problems we've been doing. During the school year, the girls' basketball team is scheduled to play 12 home games. You want to attend exactly 10 games. How many different combinations are there? Well, there's 12 home games and you're attending 10 of them, but the order which you attend the games does not matter. So to figure it out, all you have to do is 12C10, and when you do that on your calculator, the result is there's 66 ways to attend exactly 10 games. Example 4B. You have the same situation where you have girls basketball team scheduled to play 12 home games, but this is a little different. You want to attend at most 3 games during the season. How many different combinations are there? Well, in order to attend at most 3 games, you have to either attend 0 games, or 1 game, or 2 games, or 3 games. Any one of those situations will consist of at most 3 games you're attending. Well, in order to attend exactly 0 games, that's 12C0, because there's 12 games and you're choosing to go to none of them. But then 1 game would be 12C1, because there are 12 games and you're going to choose to go to one of them. 2 games would be 12C2, and 3 games would be 12C3. Since these are all the possibilities and we have or, we must add them all up. So in order to figure out how many possibilities we can attend at most 3 games, we need to add up 12 choose 0 plus 12 choose 1 plus 12 choose 2 plus 12 choose 3. When you actually write out those numbers, it's 1 plus 12 plus 66 plus 220. And when you do the addition, that comes out to 299 possible combinations of attending at most 3 games. You're in the same situation with 12 home girls basketball games, but this time you want to attend at least 10 games. How many different combination of games can you attend? Well, at least 10 games means you either attend 10 games, or 11 games, or 12 games. Just like before, you need to figure out the combinations for each of these and then add them up. So attending 10 games would be 12C10. Attending 11 games would be 12 choose 11. And attending 12 games would be 12 choose 12. Since these are all the possibilities for at least 10 games, either 10 games or 11 games or 12 games. So when you add these up, you have 66 plus 12 plus 1. There are 79 possible combinations of attending at least 10 games. The video is over, but it's your turn to practice problems. There are 6 practice problems on the back of the notes, and I would like you to solve all of them and check your answers with the solutions on Haiku.